I'd like to start by showing you what my goal is. Sometimes I'll do this. I'll go to the very, very last slide and show you what I want to accomplish. We're going to try to solve some questions that look like this, or this. Now, that's our goal. So as I show you our goal, a couple things hopefully come to mind. First of all, these are equations. How do we know they're equations? They have an equal sign, right? And whenever you see an equation with an equal sign, our job is to solve for what x is equal to. So by the time we're done, we should be able to say x equals negative 23 over 4, whatever the answer happens to be. Okay. But there's one more twist to this. These are also quadratics. And we know they're going to be quadratics because quadratics have a degree of 2. Which makes things challenging because we haven't up till this point yet learned how to solve quadratics. You have learned how to solve linear equations. I haven't used that terminology before, but that's actually what the very first one, number 27, was on your worksheet. So does someone happen to still have it nearby? Can someone read me out number 27 real quick? Yeah. 2x plus 8 equals
4x minus 8.
Okay. So this is something that we have learned to solve so far. What's the degree of this thing, though? 1. Because there's only, I mean, we don't write it there, but there's implied a power of 1 right there. So I need to teach you a new skill today then, how to solve things. Solve, meaning an equation with an equal sign. We're trying to get what x is equal to, but it's going to have x squareds in it. And that makes it more challenging because you can't put x's with x squareds. It's not possible. Here, though, we can group our like terms, right? We can maybe subtract 2x from both sides. Get rid of that little mess right there. We can add 18 to both sides. Get rid of that little mess right there. That's 26. That's 2. Divide by 2. Divide by 2. I need you guys to be able to do what I just did right there almost as fast as I did. Like that needs to be second nature. Okay. With both you guys in grade 10 and the grade 10s I just had, and with you guys, I've been using the analogy of the Jenga blocks. If we want to be good at math, we really need to build at a base level. And so if you are struggling with algebra, like if what I did there, that went over your head. Like if you're not even if you're on stage 1 where you couldn't follow that, we got work to do, okay? Please, that's not a bad thing. I'm willing to work with you as much as you need, but if you're missing the entire first level of the pyramid, and we can't do basic algebra, that's going to topple over real fast, right? Okay. The second thing I need you guys to be able to do is factor, okay? Which is today's topic. What is factoring? Factoring is actually just the opposite of expanding. So you know how I've also been making you work on a lot of foiling where you do this times this times this times that? That's another skill that I need you to get pretty good at, right? Where is it okay to make a mistake once in a while because you screw up and you forget what 5 times 6 is? Because I did that, right? Like that's okay, right? But if you don't actually understand on a general level how to do these questions, we got to fix that because I need you to be able to foil these things without making more than just like a whoops mistake, right? Because today our goal is to go backwards. Rather than take this and go there, we're going the other way instead. And this is a skill that I've actually already seen. A lot of you know how to do this because you learned it last year. But I'm going to take this right from the very, very, very beginning. So I apologize if I kind of bore you for a bit. If like, you know, I know how to factor. I did it last year. But I'm going to show you right from the beginning how this factoring concept works. So, a little bit of a review before we get there. Just in case I use these terms, have you guys heard the words polynomials before? Yeah. Poly, more than one. Nomials, more than one number, essentially. Okay. Degree is basically what's the biggest exponent. Okay. And we can write them either in a standard form or a factored form. Do you guys use that terminology? That one might be new. This right here, if you want to go back a slide, is standard form. Sometimes standard form is called general form, depending on who says it. Essentially, standard or general form means start with the squared term, then write the x's term, then write the constant term. If you had a cubed term, it goes in front. If you have it to the power of 4 term, it goes in front. This one over here then would be factored form. where essentially it's broken up into groups of some kind. There could be 2 groups, 3 groups, 4 groups. It could be something like this. That's in a factored form. Maybe I'll use the words monomials, binomials, and trinomials. You guys probably heard those words at some point before, right? Monomials have just like one set to them. Binomials and trinomials are different because there's always a plus or minus sign in between. Okay. That one little symbol makes all the difference in the world. These things have to be not like terms. These things have to be not like terms. Because if they were like terms, you'd put them together. Can you put 5 x's with 1? Well, let's say it was 1x. Then you could put them together. You would make it 4x, and it would be back to being a model. So it's very important to see the difference between this guy not being able to go with that one, also not being able to go with that one. So here's the fulcrum of our lesson. You guys, over the last day and a half, have been learning how to go this way, how to FOIL this stuff. Today, we're going backwards. Does that make sense what the goal is? Okay, before I actually get to the nitty-gritty of the factoring, I actually want to show you why this is useful. Sometimes I think in math, especially, we just teach you something and say, no, this is important. And we say, in the future, you'll know why. And I think last year in grade 10, you were shown how to factor, but you might not have been shown where it's useful. Okay? I'm actually going to start with showing you why factoring is useful. And then after I show you why the factoring is useful, then I'm actually going to go back and remind you how to factor. And so in doing so, I'm actually going to show you an example of a question that's a quadratic that we're going to try to solve. This has actually got the answer already here on there. So I'm just going to try to walk you through the point of it. Here is a quadratic. It's a quadratic because there's a power of 2. Are any of these terms right here able to go together? No. That makes it really challenging to solve for x. Because how do you solve for x when you have an x right here and an x squared right here, and they physically are not allowed to combine? Well, if you can factor, and that's a big question, like if we can factor it, so I'll talk about how to do that in a second, but if we could factor it into 2 binomials, see if this logic makes sense. See how it's equal to 0 on the side? But these factors are being multiplied by each other. How do you multiply numbers and make them equal 0? Well, the only way you can multiply numbers and have them equal 0 is if the number that you try to multiply by, one of them is 0. Does that make sense, that logic? Right? If it's going to equal 0, I'm going to change this. If you can factor, so we'll get to that, it means that either x minus 6 must have been 0. Or it means that x plus 7 must have been 0. One of these 2 things must have been 0. Like say 0 times 7. That'll work for 0. 11 times 0. That'll get you 0. So essentially the point here being is that we actually now created 2 linear expressions. When I draw some arrows here saying, well, either this x minus 6 must have been equal to 0. Well, if I add 6 to both sides, I get 6. There's an answer. I got an answer, right? Isn't the whole goal of solving to get what x is equal to? But here's where this gets a little bit tricky. There's more than one answer. Over here, what if this little factor, little group right here, what if it had been a 0? We don't know which one was 0. One could have been. The other could have been. They both could be. If this little bit had been equal to 0, I again have a nice linear expression. And how do you solve something like this? You just minus 7 from both sides. Apparently, x could be negative 7 as well. Big twist then. Sometimes there's more than one answer. And that's one of the big fundamental things we're going to talk about this year in algebra. For like the last, 10 years of your lives, you guys have always been told to solve for x. X is 5. Well, today, x is 5 or 6. There's actually more than one answer sometimes. And that really takes a second to wrap your mind around. Let me show you another example here. Let's say that you were given this right here, and you were asked to solve this. Now, again, I'm going to talk about how to do the factor step in a bit. But let's assume that you can go from here to here. Okay? If you don't know how to make this first step, don't freak out. That's not the end of the world. But the point now being, it's equal to 0. Well, the only things at times to give 0 are zeros. So it means that this thing right here must equal 0. Well, hey, now it's a nice linear expression, something where all I have to do is just add 3 to both sides. Apparently x is 3. Let's check that. Let's throw some 3's in here. 3 squared is 9. 9 times 2 is 18. 3 times 7 is 21. Does that work? Yeah, it does, doesn't it? So apparently that is an answer. But the big twist today is no longer is x sometimes only just one answer. Sometimes there's more than one. If we agree that that's a factor eventually, that same logic applies over here. Either this thing must have been 0, or this one must have been 0. I don't know which one. They both could have been 0 for all we know. Well, it means that I can write a new statement then. This thing, 2x minus 1, if it's equal to 0, is now linear. How do we solve it? Add 1 to both sides. And you get this. Divide by 2. Apparently, 1/2 works as well. So I'm kind of starting at the end in mind here. Our goal is to work on our factoring, because if we can factor, we might be able to create a scenario here where we can actually separate it into parts. So let's try these ones here. Just some examples. This is already factored. And conveniently enough, it already equals 0. That's good news, right? What is the only way to make something equal 0 if it multiplies by each other? They have to be equal to 0. But like the whole thing has to be equal to 0. So it means this whole x plus 5, it must be equal to 0. That's the only way for this thing and this thing to somehow times by each other to make a 0. Well, this is just good old-fashioned grade 8 algebra. 7. Minus 5 from both sides. X is minus 5. Think about that for a second here. If you had minus 5 right here, minus 5 plus 5 would give you 0. Now go over here. Minus 5 minus 3 is going to give you minus 8, right? I could care less about the minus 8. If this section right here is 0, who cares what this is equal to? It's going to equal 0, right? But is it the only answer that works? No, and I'm going to say this a lot over the next couple of weeks here. We're going to start taking math to a place where there's more than one right solution. And I actually really like teaching that because that's sometimes the way life works. Sometimes there's more than one right solution, right? You could win under these circumstances or these ones. Okay, the same logic applies over here then. X minus 3 must also have a chance of equaling 0. Well, if I add 3 to both sides with our grade 7 algebra, apparently 3 also works. Try it out. Those kids in the hallway are loud. Same with 3 plus 5 right here. 3 plus 5 would give us 8. Okay, that's not the useful part, right? But if we did 3 minus 3 right here, 3 minus 3 would give you 0. That 0 times by who cares what's over here will give you 0. Okay. So this is the fulcrum behind how we solve quadratics. We actually have to combine a whole bunch of previous skills, hence the analogy of the Jenga blocks. Right? In order for us to do this, we're going to have to be able to do basic algebra. We're going to have to be able to expand, and the one thing I've been skipping over, which I will get to, is we need to be able to get it to a factored form. If we can get it to a factored form, though, we can solve it. Okay. After a while, some kids start to see what the answers are without even doing work. Like, for example, what number right here is x going to equal? Yeah, right? Because you can start to see, heck, 5 minus 5 equals 0. So after a while, I'd be even okay with you just going right to, well, the answer right here is 5. This one over here is maybe a bit more challenging because it's not quite as obvious. So, I mean, it doesn't hurt to get in the habit of just writing it out. Well, the 3x plus 1 must have equaled 0. The whole shebang right here is a 0. So, subtract 1 from both sides. Divide by 3. Apparently the other answer is negative 1 over 3. So, big twist. More than one right answer. really need to have those algebra skills down pat though, right? Like I said, if that bottom level of the Jenga tower isn't working, please let me know. I will work with you on it. That's why I made these duotanks. Because after the last couple of years of me being a teacher, I realized that sometimes that's what kids are lacking. Sometimes I recognize that what I teach, the new information, I find that kids pick up on that. But they're hampered by the fact that last year or the year before that, truthfully, you goofed off, you didn't pay attention, and like you recognize that my algebra skills are not where they need to be, right? And so it's not meant to be like trying to shame you. I'm trying to say, fill in the holes. Right? If you know there's a gap, work on it, right? Okay, so now kind of skipping back again. If you kind of get the concept about how the big picture works, you have to know how to factor. So I'm going to give you guys my grade 10 factoring lesson. So I like to break things up into 4 different types of factors, 4 different like types. I don't know whether Juan did this with you or not, so there should be a lot of overlap, but this may be kind of a different way of looking at it. Let's see how this goes. Common factors are ultimately the only kind of factors that exist, actually. Finding things that are in common. But if you know how to do common factors, I think there's 3 other categories, things that I like to call simple trinomials, where there's 3 terms. I call them simple because there's a 1 in front. That's why I call them simple. It gets a lot harder if there's like a 3 in front. And there's another one called the difference of squares. So let's see if you guys remember this. So let's start with common factors. The common factor basically says, what's the same between both terms? What's the same in both of these? 3 and x. There is both a 3 and an x in both of them. Sometimes students tell me that the thing in common is a 2. And although you're kind of right, it's not the 3 that's in common, but when you're done, 2 happens to be one of the leftover bits. So hopefully this looks familiar where you say, okay, well if I take a 3x out, if I take 3x out of x squared, there's an x left. And if I take the 3 out of the 6 divided by 3 is 2. So hopefully this is something that you're fairly used to. You've done that at some point. This, at its core, is what factoring looks like. Every other type of factoring is based on this. But you may have learned like some tricks or some other techniques along the way. So I'm going to review some of those. So I call this one a simple trinomial. You'll recognize it because there's 3 terms. What I'd like to do is I'd like to show you the very, very long form way of how this gets factored. And then afterwards, we're going to do like, you probably know like the shortcuts. So if you know the shortcuts, don't feel like you have to do this every time. Ultimately, the way you factor anything with 3 terms is you try to break it up into something with 4 terms.
Yeah.
I did dial 3501.
Okay.
Jeez.
3501.
You're supposed to check out? Ultimately, any 3-term trinomial, actually what we'd like to do is make it into 4 terms. What we're going to do is we're going to take this middle term here and we're going to break it into pieces. Now, in order to figure out what those pieces are, there's a method that maybe you were shown where you have to look for numbers that add and multiply to give values. Is this look familiar?
Yeah.
Okay. So we need to look for numbers that add to give 3, because 3 is the middle number. And we multiply to give 2, because 2 is the outside number. Those numbers are going to be 2 and 1. And it doesn't actually matter which order you put them in. But what we're going to do is we're going to take this 3x right here, and we're going to break it up into a 2x and a 1x. Doesn't 2x and 1x add to give 3x still? Yeah, for sure it does, right? But what we need to do is we need to break it up into 4 pieces. Okay. It's actually still a trinomial. I know there's actually 4 terms sitting here now, but really these 2 terms, they could go together if we wanted them to. Now we do common factoring, but we do it in 2 stages. So we do is we cut this thing in half. This is how I like to show it. And we just look at just this little bit right here and say, what's in common? What is the same between an x squared and a 2x? X? Not the same. Well, what's the leftovers? X plus 2. Well, we do the same thing over here. We ask, what's the same between a 1x and a 2? Yeah, actually, that's the right answer, 1. There's actually nothing other than the number 1 that's the same between them. So I'll write like a plus 1. And it actually ends up making it so that there's x plus 2 left. if you do this correctly, you might notice something then. This stuff in brackets is the same. And that's a good sign. It means you're doing it right. In a way, I'm now going to pretend that this stuff in brackets, just temporarily, I'm going to call it y. We could factor this again. Because look, this thing over here has a y. This thing over here also has a y. Only it's not actually y, it's bracket x plus 2. But this side over here has an x plus 2. This side has an x plus 2. So if I factor out that piece, in a way, pretend it's a y. There's a y in both of them. What's left over? Well, there's an x on this one that wasn't accounted for. And over here, if I take out the y, there's a 1 over here that wasn't accounted for. But it's not actually y though, right? The y is x plus 2. Hey, look, it's factored. You're never going to do it that way again. Because you probably learned a shortcut at some point. You guys know what the shortcuts you've learned are to simplify that a little bit? Usually once you find those numbers right there, not usually, always, when you find those numbers right there, see how there's a 2 and a 1 right here? And a 2 and a 1 right there? You can go right to the answer. Yeah. Okay. So what I was trying to do here is show you why this works. But truthfully, like, I would be fine with you doing this x squared plus 3x plus 2, saying what adds to give 3, what times this to give 2. You'd say 1 and 2, 1 and 2. And if you went just right to x plus 1, x plus 2, that's it. Okay. But at its core, the reason why that works, the reason why you can skip all those steps, is because what you're doing is you're splitting it into 4 terms. You do a common factor here, a common factor here. You discover, hey, this is the exact same as each other. I just temporarily called it y. You factor it out in front, and then you end up getting your 2 factors. Is that familiar? It should have been a big part of what you did last year. Right. These ones here are a little bit more challenging. You throw that number 3 in front right there, and most people can't just look at it and see the answer the way you did on the last one. Some can, but chances are you have to kind of go through the same sort of process. So what I usually suggest is we need to look for numbers that add and multiply. The twist, though, is this middle number right here, we're going to break it up into a couple of different values. Twist is the numbers that we're looking for are just slightly tweaked. For sure, these 2 middle numbers here, they have to re-add to 7. Guaranteed, right? Because if I work back upwards, it needs to be a 7 right there. But it's not numbers that times to give 2. That's not correct. You guys know what number you are looking for to multiply to? 6, yeah. The 6 is because it's 3 times 2. The first number multiplied by the last number will help you this work out. So it's actually 6. Truthfully, we actually did this process on the last question. We were looking for numbers that add to give 3 times to give 2. But 1 times 2 is 2. So you're actually doing it all along. After you learn the basics of factoring, often we just skip these little details sometimes. Okay, so we need numbers that add to give 7 times to give 6. 1 and 6? Yeah, 1 and 6 will do. It doesn't matter what order we put them in. But what we're going to do is we're going to take this 3-term trinomial. It's still technically a trinomial, but we're separating it into a 1x and a 6x. And if you flip-flop the order of those, it'll still work. I like this method. It's very tried and true. If you understand the basics of common factoring, it's very reliable, is the word I'm looking for. You won't make mistakes if you do it this way. If Quan showed you other ways, and it works for you, that's fine, by the way. But to me, this is very reliable now. So, cut it in half. Do a bunch of common factor. What's in common between 3x squared and 1x? X, that's all that's in common. The leftovers then are 3x plus 1. If we do this correctly then, what this factor is right here should be the same as this one here. So 6 and 2 have a 2 in common. Don't say 3. 3 is the leftover part. So there is a 2 in common, which gives you 3x plus 1. Hey, look, that's the same. Well, once you figure that out, in a way, from both this half right here and this half right here, there's something in common from each half. The thing in common on both halves is the 3x plus 1. The leftovers then is this x right here and that 2 right there, which it's going to imply it's a plus 2. If there's a negative out front, it's okay. There, now I factored it. I find that's a very reliable method. Well, and at its core, really all you're doing is 3 sets of common factors. This part right here, you're common factoring it. This part right here, you're common factoring it. Once you get to this set right here, this little bit will also be in common. And so as long as you know how to common factor, you can solve this. But if you have like a shortcut or some sort of method that you've learned otherwise, we can use that. Here's the last one. This is the difference of squares. There's also a really good shortcut for this, but I want to go through why this works first at a very, very core level. So, are there 3 terms here? Well, if you cheat a little bit and write it like this, yeah, no, there are. Because in a way, there's 1x squared, there are no x's, and there's a minus 81. The exact same process I just showed you on all the last examples really still applies. There's ways to shorten it up a little bit after you get better. So what we need to do is look for numbers that add and multiply together. What does it need to add to give though? 0, yeah. The middle term, since there's nothing there, it needs to add to give 0. It's actually really hard to have 2 numbers add to give 0. The only way to have 2 numbers add to give 0 is if it's the same number, one of them is positive, one's negative. If it's negative 5 and plus 5, that'll add to give 0. Negative 6 and plus 6 will add to give 0. So we're looking for numbers that times to give 81. Well, not a lot of things times to give 81, right? 9 and 9 will. So if we make one of them be a plus 9 and one of them be a minus 9, that'll work. Some of you might already know the shortcut though. The shortcut, I'll even give you the answer we got at the bottom here, is it's just x plus 9, x minus 9. And truthfully, if you get that, you just want to go right there. If you want to go just right there, that's fine. But let me show you the math as to why that works, as opposed to just telling you, here's an answer. What you would then do is you'd take 1x squared, you'd add 9x, you'd subtract 9x, and subtract 81. Because doesn't 9x minus 9x really cancel out to be the nothing that we didn't even bother writing there? You cut it in half, you do your common factor. So on this side right here, there's an x in common. Leaves you with x plus 9. Over here, both of them are negative. So I'm going to pull out a negative 9. And it actually ends up being, again, x plus 9. Hey, look. There's x plus 9s in both locations. It means that the x plus 9 can get factored out. The leftovers are this x and the minus 9, which are right there. I don't really care how you factor. There's different ways. I'm showing you one method that I find is really reliable. But long story short, in order to solve what we want to do today, you need to be able to bridge this gap right here, which was right here. If I give you any sort of quadratic, if you can bridge that gap and factor, there's a good chance you'll be able to solve. And you'll probably get 2 answers, actually. So, why don't I leave this slide for right now? If you feel like you need more practice on factoring, you can do this slide later. I have a book full of things to practice factoring. But why don't we try to move on to the core of what we're doing today then? Our goal is to solve things like this. So, looking at these questions here, we have to solve. Yeah, take our time. How do we know we have to solve? There's an equal sign. Yeah, an equal sign means we can try to solve. Our goal at the end of the day is to figure out what x is equal to. The challenge, though, is, do any of these terms have the ability to go together currently? The answer is, well, no, they don't. None of them are like terms. So the first trick, then, is that for our little magic trick to work, it has to equal 0. That's the very, very first condition. We have to make it equal to 0. Because if we try to make it equal negative 10x, lots of things can equal negative 10. 1 and 10, 2 and 5, you know what I mean? You can even use decimals. But if we can make this thing equal 0, the only things that equal 0 are zeros. So I'm going to add 10x to both sides. So that I get x squared plus 10x minus 21. And I'll make it equal to 0. That's condition 1. If it's not equal to 0, make it equal to 0. However you need to do that. It's quadratic. We need to factor it. So maybe I'll just go up to the side here. We need numbers that add to give 10, multiply to give minus 21. That actually doesn't work, does it?
You need a negative.
Because we need a negative. You know what? I might have a typo in this. Let's pretend that's a plus 21. Because I might have made something that doesn't actually work, which we're not ready to cover yet. So pretend it's a plus. I think I typoed this thing. Because if it's minus and minus, that wouldn't give plus 10, right? The only things that give 21 are 1, 3, 7, and 21, right? But if I did 7 plus minus 3, then that wouldn't give 10, right?
Yeah, because 7 minus 3 is 10.
7 minus 3 is 4. You good now?
Yeah.
She's thinking.
Okay. It's okay. I did it yesterday. I couldn't do 5 times 6. Okay. I think I have a typo. Make that a plus sign. If we make it plus 21, are you guys in agreement then we can go with plus 7 and plus 3?
Yeah.
Okay. I don't need you to do the long form here then. If you know the shortcut and know how to pull this off, your answer then is one of them is x plus 7. One of them is x plus 3. Okay. So this is the big step. I'm going to put a big star next to this. If you possess the ability to factor, again, that's a brick on your Jenga table, right? If you know how to do that factoring bit, well, from here, here's how this looks. Either the x plus 7 must have equaled 0, which means it's minus 7, or the x plus 3 must have equaled 0, which means it's minus 3. You can see how the tower gets built. We have to have some pretty good algebra skills. You also have to be able to factor. If we can put those things together, we can now solve questions that we didn't have the ability to before. That makes sense? Let's try the next one. Okay, so for this one right here, right off the bat, this actually requires even a third skill. What does x plus 1 with a squared sign mean? What does a squared sign imply? It means it's written next to itself. A squared sign means that there's 2 of them right next to each other. So before we even do anything else, we need to FOIL this thing. So this is kind of gross. I now need to FOIL. So you guys can see why I've been making you practice FOILing the last couple of days too. So I'm going to get an x squared, an x, another x, a 1, and make it equal to 9. Can we solve it? Well, it has an equal sign. Okay. But what does that equal? 0. Doesn't equal 0. Minus 9 from both sides. There we go. Not equal to 0. So what's my quadratic? Well, it's x squared. There's 2 x's sitting there, right? And 1 minus 9? Minus 8. This may seem kind of weird because we just finished taking something from a bracketed form and turning it into a expanded form. And now we have to go right back again. But here's the difference. We couldn't work with this because it was equal to 9. It needs to equal 0. So we had to FOIL this stuff out, make it equal to 0, and now we're going to have to take this thing, and again, this is the star move. We need to try to find a way to re-put it back into some brackets. We need numbers that add to give 2 times to give minus 8. Numbers that add to give 2 times to give minus 6. That'll do, yeah, 4 and negative 2, right? Okay. So it means that right here I get x plus 4 and x minus 2. Okay, well then the last logic step is either this thing must somehow equal 0, or this thing must equal 0. If you'd like to, you can probably go right to the answer here, but I'll just show the work again. So it means that x plus 4 must have equaled 0. Subtract 4 from both sides. Minus 4 will work. Let's check our work. I've been doing that very much recently. If you put minus 4 in and add 1, it's minus 3, right? Minus 3 squared? Minus 9. That works. But what about this? Here, if x minus 2 is equal to 0, if I add 2 to both sides, then 2 is also going to work. 2 plus 1, 3. 3 squared? Yeah, that works. So it's a very groundbreaking change. For so many years, you've always been told there is a right answer. I'm here to tell you now, sometimes there's more than one right answer. Eventually, we're going to talk about a scenario in which there is no right answer. Kids hate that one, but we'll get to that in a second. Maths really starts to change at a certain point here, where it becomes a little less, I mean, it's still black and white in some ways, but it really changes compared to what you're used to. Okay, I don't know about you guys, I've been sitting for way too long, my butt hurts. Why don't you guys take a 2-minute wiggle break before we do, we have just one last example? 2 last examples. Okay. Why don't you guys take 2 minutes, grab a drink, get a wiggle, move, because I'm tired of sitting. Can't imagine you guys are. Let's do the last 2 examples.
So, is that, that's grade 9 math?
What they were doing it?
Is that,
Well, I mean, I don't know when they learned some of these skills for the first time. Really, this is the culmination of putting them all together, right? So they must have done the linear algebra at some point, right? For sure, the expanding and factoring is grade 10. This is a big unit in grade 10 on factoring. I think expanding must be grade 9. But like, this is where the Jenga pyramid kind of comes
they
in.
learn FOIL in grade 9.
Did they? Okay.
I think so.
I think so. For sure in grade 10. And they learn factor in grade 10.
Oh yeah, these guys are 11.
These are 11s.
Right, yeah, okay.
So, but I mean, really, most of this is now just taking a whole
This
bunch
is
of
all, so this is not new material for grade 11 math.
It is, in that it's the first time they put it all together. Right? It's a culmination of a bunch of little skills, right? But they've never been put together in this sort of way yet, right?
Yeah.
So, because yeah, algebra should go back to
So the putting of it together is the solving of 4x
in a quadratic.
in a quadratic.
Because previously they've only ever solved linears,
Yes.
right? But if you can put all these pieces together, hence the Jenga puzzle. So that's the problem, right? Is as soon as you start pulling out, well, you can't multiply 2 digit numbers together. I can't deal with integers. I can't do this, right? The whole thing comes falling down.
It's kind of interesting to watch how you can say something and not have to explain why you're doing it. Like back in grade 7 math. Like, wait. 2 plus 1 is 3. 3 squared. 4 is 3 squared is 9. You'd have to show 3 squared is 9 and 9 equals 9.
It's always hard to find that level where it's like, well, what do you not need to explain? Because there's sometimes where, like, when we get to the factoring thing there, I won't even explain. I'll just go with factoring. Right? And just be like,
and
what I need to possess.
Yeah, and what I found in teaching, like solving equations, like 2x plus 1 equals 3.
Some
Grade
kids
7. Some kids, details actually comes them off. They just want to solve it in depth. Other kids, they need to show exactly why everything works.
One thing that I'm really starting to work on, because I see it, the more I've seen this new curriculum, is that the skills exist, but some of the basics, fundamental building blocks below just haven't been sunk in enough. And so I find that kids have been able to prove at one point they could factor, at one point they could do algebra, but it hasn't been built. The house, the foundation isn't strong enough that it's been done concurrently. And I feel like our outcome-based assessment has hurt kids very badly in math. Because all we do is we say, well, you were able to accomplish this. But it's very, very different, right? And the house topples over at a certain level
Yeah.
because you're doing multiple calculations, right? Like
Yeah.
right off the bat here, if they don't know what 2 times 4 is in their head,
Yeah.
you're screwed, right?
Yeah.
You know, but I mean, some kids will still need to work on that.
Yeah.
2:30. So you get 20 minutes. Okay, I'll take up when you need to. I'd go sign up with Shirley in the office. Yeah. But I mean, if you get a dentist appointment, then you go. Something 10 minutes. Remember, I record the video here, so just watch the last 5 minutes of the video. Okay, guys, I've got 2 last examples. So I kind of showed you these ones to begin in class. I was even just saying with Mr. Bonnet here, really, everything that we've learned today isn't new. You guys learned how to do algebra back in grade 7. You learned how to expand in grade 9. Last year you learned how to factor. All we're doing today is putting all these little skills together, right? Hence the Jenga analogy. If you can't multiply, you're going to have a problem. If you can't deal with negative numbers, you're going to have a problem, right? But putting all these little skills together takes a problem which looks kind of intimidating. That looks scary. And I mean, let me show you some of the things we're going to do in the next couple of weeks. Ooh, this one looks like fun. That looks intimidating, doesn't it? Right off the bat. That doesn't look like fun. That looks like a challenge. That being said, I promise you, you guys actually, right now, possess all the skills to solve it. You just never learned how to put them all together. Yeah, you kind of give me the take it back look. But I promise you, you guys have all the skills. One of the things you're going to need to do to solve this question right here is factor that piece right there. You guys learned how to factor last year. At a certain point, math doesn't actually become necessarily new. It's more just like, what if I take this skill and put it with this skill? What can I accomplish? Does that make sense what I'm saying here? Oh. And so today we're really learning on, well, what if we take algebra and combine it with factoring? What can we do with that? What if we throw in some expanding? So I'm going to go back to our last 2 questions here. Whatever those were. All right. So before I start, right off the bat, I know we're solving because we got an equal sign, right? What skill do I need to take out of the Jenga pile and apply? What's the first thing that we could do? Yeah, FOIL/expand, right? So that's a skill that you've all learned at some point. You might need to refine it and practice it, but you've all learned this, right? So let's FOIL. You're going to get x squared, 2x, 1x, and 2. And I'm going to start speeding that process up, right? Because individually, that's a skill you know. If you need to work on it, work on it. On the other side, you're going to have 8x minus 4. So, expanding foiling skill. In order to solve a quadratic, the big requirement is we need it to equal 0. It's a really clever trick, actually, right? Numbers that equal 0, the only way they multiply to equal 0 is that individually they were 0. So, I think the best option is probably to move everything that way. So if I subtract 8x from both sides and add 4 to both sides, what's left? Well, this is your grade 7 algebra. Again, a skill that you probably possess. You might need to work on it. 2 plus 1 is 3 minus 8, negative 5. And then 2 and 4 is 6. So individually, if I just gave you just a question on algebra, that's what we just did. Now what skill do we need? Factor. We need to factor. So in order to factor, this is what Quan would have showed you last year. So we need numbers that add to give negative 5. Numbers that multiply to give 6. Good job. That's it, yeah. -2, -3. -2, -3. again, if this step in the process is where you get lost, this is why I made the duotangs, right? Because you need to work on that. Otherwise, there's a Jenga block missing. So you can take this, with this particular shortcut, directly to x minus 2 and x minus 3. Then the last step here, the only way that numbers can multiply to equal 0 is if individually one of them was 0. So how do you make this thing right here equal 0? Yeah, 2. How do you make this thing equal to 0? We have 2 answers. As we get further on in math, sometimes we'll have 3 answers, 4 answers, 5 answers, possible. Eventually we'll talk about a scenario where there are no answers. And that's a very strange thing for students. It doesn't mean that the question is broken. It doesn't mean that you made a mistake. But sometimes there are puzzles that are unsolvable. And there literally is no solution. Not that the answer is 0, but that it's an unsolvable puzzle. We'll get to those ones too. Let's check our work. Go for it. If I put a 2 right here and a 2 right here, that makes it what? 4 times 3, that's 12. If I put a 2 right there, it's 4 minus 1, that's 3. 3 times 4 is 12. Checks out. I'm sure the other number works too. So let's try one last question. Again, it looks a little intimidating perhaps, but we have worked on all these skills individually. What's our first problem? What? Okay. We gotta FOIL some stuff, right? Like this stuff right here needs to get FOILed. Over here, this squared symbol means that it's written next to itself, which means I'm gonna have even more foiling to do. So long story short, I need to FOIL everything. I have an analogy sometimes I use. The analogy is think of a rope. This rope right now has a whole bunch of knots in it. And in order to undo all of the knots, I'm just going to FOIL everything to death. That's me untangling the rope. Then I make it equal to 0 so that I can actually tie the proper knot in the rope by refactoring it. So right now I need to untie by FOILing it all out. So I'm going to go like 3x plus 6 next to x plus 2. It'll be 3x squared plus 6x plus another 6x plus 12. So that's all the stuff in red I just did. In purple, if I factors or FOIL it out some more, you'll get minus 13x minus 26. I went through that fast, eh?
Yeah.
I need you guys to have that skill. Okay? So granted, I know I'm zipping through this, but if that's not something that you can follow, like if that went over your head, we gotta work on it, okay? Because that's just one of a million steps we're doing, right? But think of it like a rope. Right now, this rope is a tangled up mess. There's all sorts of stuff going on there. So whatever it takes, however it works for you to practice your expanding, expand. So minus 13 times x, is that minus 13x there? Minus 13 times 2, is that minus 26? This x plus 2 squared, I wrote it next to itself, that's what squared means. I FOILed the 3 and the x to give here, the 3 and the 2 there. And then I FOILed this guy to get all these terms. Hope I did it right. So the rope's now untangled. What does it have to equal though? 0. So to make it equal to 0, I better minus 12 from both sides. Okay, let's combine like terms. We've got a 3x squared. That's this guy right here. In terms of x's, 6 and 6 is 12. Minus 13 is negative 1. And then in terms of our numbers, our constant terms, here there's a plus 12. Here I subtracted the 12, that kind of evens it out, right? And then there's a minus 26. Is it able to follow up to that point? Okay. So if you like my rope analogy, Here, it's a tangly mess. Here we've untangled it. Now we have to tie the proper knot. In terms of tying the proper knot, we need to foil it so that at some point it looks very nicely like this. We need to have the skill, though, of factoring. Not just factoring anything, though. This is factoring those stupid ones that have a 3 in front. Those ones suck. Like, they really do, right? So again, if you know for tomorrow, whenever I give you some work time, right, even focus time, if you know that factoring with a number in front is not your strength, practice that. Ask me for help, we'll work on it. So I'll go a little slower on this one. We need numbers that add to give -1. There's a -1 right there. We need numbers that multiply to give whatever 3 times 26 is. What is 3 times 26? 88? 78? 78? Okay. 78, that's not an easy one. Never got this. Okay, so here's what I do sometimes then. I'll go 78 divided by 1 to 78. Do 1 and 78 differ by 1 though? No. 78 divided by 2 is 39. Do 30 and 9 differ by 1? 78 divided by 3 is 26. But 3 and 26 don't differ by 1. 78 divided by 4 to give 19.5, that's no good.
What about 8 and 7?
Let's try that. 78 divided by 8. Oh no, 8 and 7 is 56. That doesn't work. Anybody find anything? $78 divides by... Yeah. So this is actually the scenario that I was hinting towards earlier. Sometimes things can't be factored. Now, I'm going to show you guys next week what to do in a scenario like this because we have a backup plan. But this is going to take a little while to sink in. Sometimes the answer is, it can't be solved. Now, sometimes kids really get frustrated by this because there's a difference between it can't be solved because I made a mistake or I didn't pay attention in class and so I can't solve it. And sometimes the answer is, it doesn't matter who you are. There is physically no answer to this question. And that's actually what we came to for a problem right here. Since this thing cannot be factored, there's a very good shot that there are no answers that make this work. If we tried to plug a number in for x right here, doesn't matter what number we pick, we'll never find a number for which we put in x, and we'll make it equal to 12. Let me give you a different example of something on this where maybe you've seen it before. Find me what x is. Can you take a number, square root it, and have it equal -2? I don't think so, right? Or maybe here's another one here. Let's try this one right here. You can't. This one's probably better. Maybe I'll do this one here instead. Is it possible for us to somehow have a negative under a square root sign?
No.
Right, that's like an invalid thing. Here's another one you've learned about. What if it was x divided by 0 equals 7? Well, you're not allowed to divide things by 0, right? So there are actually scenarios in math where the answer is, and I'm going to say this a lot, the answer is, there is no answer. So for today, we're actually going to have to leave that question wherever it was, right here, because from here to here, we cannot factor. Fortunately, we're going to learn about something next day's lesson called the quadratic formula. And it's a formula that we can use that sometimes helps us solve this problem. Sometimes it works, sometimes it doesn't. So we will get to this next week, Monday. So it's weird to kind of leave this question right here as saying there is no answer. Let me just recap though what we would have done. Let's say it did factor. Let's say it factored into x plus 2 and x minus 1. Could we have solved it from there? Yeah. The answers would have been x was 1 and x was minus 2. But unfortunately, there's a big gap right here. And since we couldn't do that, we're stuck. So let me give you a quick recap here. And I don't even know that I taught you new stuff. What I taught you how to do was put it together. In a way, it's like you're in the kitchen, you're cooking. And you've never tried putting gummy bears with bananas. It's a dumb idea. Right? But in a way, we've learned 3 skills. We've learned algebra, we've learned expanding and factoring. Putting them together, we can build a pretty awesome pyramid out of those dangling blocks. So I've said this like 11 times today. You have 2 days tomorrow now. We've got all of Thursday, all of Friday. You've also got a focus time on Thursday. So that means that you have like 3 hours. Okay? On Friday, your assignment's due. Okay? But more than just that, you practice questions in those practice journals. Right? That's what's really going to help you get better. Okay? So by Friday, for sure, finish the assignment. And I'll probably give you some more questions to put in your skills journal, other than the ones that are written on the board there. But like by the end of the week, I mean, off the top of my head, I'd sure like to see at least 20 questions in there. Of varying levels, right? Start with some easy ones, try some challenging ones, but you should have something in there as well. Does that sound good? Cool. If you gave me a form, see you later. If you didn't, find a form, get your parents to sign it. Thank you. See you tomorrow, guys.
All of a sudden it shows up.
Imagine that.